Hey everybody. Today I'll be talking about recitation 7. I'll go through the PowerPoint pretty quickly and then also look at all of the questions on the recitation 7 quiz so that any of you who are interested about recitation 7 material can look at this video and hopefully it helps. So this recitation and the quiz were prepared by TA Wansheng. If you're watching this today, I recommend that you attend his office hours later, as a lot of this material has a lot of equations, and honestly, it looks a little bit like calculus and like algebra, which is a bit intimidating. So I'm going to try to kind of delve into this material, but if it's not as clear to you, I recommend you go to another office hour today before submitting your quiz, which I believe is due tonight. So the learning goals for this recitation are to calculate the absolute and relative fitness of a population, to predict future genotypes and allele frequencies under selection, and to identify the selection type from genotype fitness. So we're looking at kind of like allele frequencies through the lens of different variables. So the first of which being natural selection and fitness. So natural selection overall is the variation in reproductive success tied to a phenotype, while the absolute fitness is the survival multiplied by the reproduction, which makes sense. We're looking at both how many more of yourself you can create, as well as how well you will survive in a given environment. Then finally, relative fitness is this W, which is absolute fitness divided by the highest or absolute fitness among the genotypes. So some conditions for natural selection are phenotypic variation among individuals, this variation affects fitness, meaning that there's differential reproductive success, and that these traits are heritable. So that there's like some sort of genetic basis. Obviously, we're in a genetics class, so that makes sense. So then some sources and filters of genetic variation are mutation and recombination. As we've talked about with homologous chromosome recombination, that increases the level of diversity greatly, which is overall beneficial for um, a population as a whole, even if some of the recombination leads to mutations that are not gain of function, more loss of function. Chances are that you're going to have a gain of function recombination event that leads to diversity that overall promotes the survival of a population. Then we're looking at genetic drift and bottlenecks, which leads to less variation, migration, which leads to more variation and homogenizing of a population, and then selection, which can be directional, balancing, and purifying. So first, let's look at absolute fitness. That's the number of survivors divided by the initial number of individuals times the average offspring per survivor. And it reflects the genotype's total genetic contribution to the next generation. Then looking at relative fitness, which is a slightly different W. It looks like a Greek letter. Don't know it off the top of my head, but um, that's the absolute fitness of the genotype divided by the maximum. So any given genotype divided by the maximum gives you the relative fitness, which makes sense. We're looking at it relative to the maximum fitness. So this sets most fit genotype to 1, and then the others is some uh, ratio between 0 and 1. Then we have a selection coefficient, S, which is 1 minus the relative fitness. And that measures fitness reduction. So looking at mean relative fitness, which is slightly different, we have this interesting equation. I'm not going to uh, just read it like it's kind of like alphabet soup, but it represents the population's overall fitness. And this selection raises the mean relative fitness over time. So even though this is a pretty complicated equation, we can see that um, it's almost like a plug and chug equation, similar to like a physics equation. As long as you're given these variables, you just have to do a bunch of multiplication and addition. So there's an example that Wang Sheng also used, which are leaf beetles. They have phenotypic variation. Different genotypes of leaf beetles confer different degrees of fitnesses. And heritable phenotypes, they have heritable phenotypes, and the variation is genetically transmitted from parents to the offspring. So there's some conditions that we're talking about in this slide with leaf beetles that I mentioned on an earlier slide. So looking at leaf beetle species that live on green leaves, um, We assume that the coloration is a Mendelian trait, so it's encoded by a single gene segregating two alleles. And we can assume that the green beetles that live on the green leaves have better camouflage so that they actually survive more. So looking here, we have A1, which is the allele for the green phenotype, and then A2, which is the allele for, I think that's kind of like a brown purplish phenotype. And it seems like A1 is dominant over A2. I think we have a heterozygote here that is colored green. So 2/4 of A1 green beetles survive, 2/4 of the A1 A2 green beetles survive, and then a slightly lower percentage, 1/4 of A2 brown, oh, it's brown beetles survive. So each surviving individual produces three offspring. So looking here, we have W as the survival rate times the reproduction rate. So each beetle produces three offspring. So we can easily calculate the absolute fitness here by multiplying the total number that survived by the offspring. So you can see A1 and A1 A2 have 1.5 absolute fitness, while A2 A2 have 0.75. Now, looking at relative fitness, which is once again, the absolute fitness for a genotype divided by the highest absolute fitness. We have the highest at W, or the highest W is 1.5. So the relative fitness for A1 and A1 A2 is 1, while the relative fitness for A2 A2 is going to be this 0.75 divided by 1.5, and that comes out to 0.5. And that 0.75 comes from, once again, its absolute fitness. So then we calculate the current genotypes and allele frequencies. So once again, looking at this Hardy-Weinberg equation, that p squared plus 2pq plus q squared equals 1. And the other equation, that p1 equals the frequency of A1 plus the frequency of A1 A2 divided by 2. We can see that this is given. The frequency of A1 is 0.49, A1 A2 is 0.42, and A2 A2 is 0.09. We can then calculate P and Q because we have 0.49 plus 0.42, which we get from these two spots, and then divide that by 2, we get 0.7. So then we could just do Q equals 1 minus P to get Q equals 0.3. So then looking at step 4, we have the mean fitness and expected genotypes. So once again, this is where the equations kind of get crazy, alphabet soup. So however, at this point, we should have all of these variables. So you see it's more of a plug and chug equation. Um, the These values for A1 and A1 A2, once again, are 1 and then 0.5 there, which we had calculated on the previous slide, on slide 12 here. So then after plugging and chugging, we see that the mean fitness is 0.955, and the expected genotypes can then be calculated with these equations. Once again, we have all the variables, and we will ultimately get these three values. So then the final step is the expected allele frequencies, which you have P and Q. It looks like you just take the square root here since you have P squared. And then Q squared. So these are going to be your final answers for finding the expected allele frequencies. And the A1 allele increases due to the selection favoring green beetles, which makes sense. Natural selection is the survival of the fittest, and one that camouflages better on green leaves will probably survive better because it won't be spotted by predators. So then interpreting selection type, here's some information that Wang Sheng included. And then finally, there's a quick summary of the modes of selection, which is directional, balancing, purifying, and disruptive. So I'll let you guys read over those. Then conditions for natural selections. Different phenotypes are available in the population. Phenotypes are heritable, obviously. And then these different phenotypes confer different degrees of fitness to individuals. So obviously, this isn't quite Mendelian genetics because there are some other factors that go into it. In terms of looking at population genetics. So then the key takeaways here are that fitness comparisons predict evolutionary change. Selection shifts genotype and allele frequencies each generation, and then recognizing fitness patterns reveal selection modes. And then here are all of the equations once again. As you can see, once you start getting to mean fitness, and then after that, the expected genotype frequencies and allele frequencies, they get a little crazy. So if you have any questions, feel free to reach out to one of the TAs regarding one of these equations. So I'm going to stop sharing my screen at this point and then share my screen for the actual quiz. Which I think, there we go. Cool. So, looking at the first couple questions, you should be able to figure these out from the PowerPoint itself. Looking at the option that best describes the fitness of organisms. Um, Using the PowerPoint, try to select the best answer here. There might be some answers that are a little persuasive in that you should pick that one, but ultimately you'll be finding the best answer. Then you're going to be matching each variable to the fitness statistic that they represent. Using the drop-down arrow here, you should be able to get that from the PowerPoint as well. And then matching each type of fitness with the equation used to calculate it. Once again, you will be referring to the PowerPoint notes as well for this. So here's a little bit of an application question looking at sickle cell anemia. And depending on the type of selection that's exhibited within this population, here you have a little diagram of how each selection should look when comparing the phenotype or trait to the frequency of the individuals. Um, that question will go over that. You're looking at two different alleles that have to do with sickle cell anemia. Then question 5 looks at natural selection is an evolutionary force that will act as both the phenotype, that will act at both the phenotypic and genotypic levels. So looking at the genotypic level, you'll be selecting the statement that's true about this, the action of natural selection. Then we'll start using the equations in the following questions. So here you are given p squared. P squared, you're given 2pq and then q squared. So ultimately, you already are given the genotype frequencies as well as the relative fitness of all three of the genotypes. So when calculating mean fitness, as well as the post-selection frequency of allele T, P, or which is P, you'll be plugging and chugging into equations that were introduced in the PowerPoint. And then you can use the example from the PowerPoint with those beetles as kind of like a guide on how you should be plugging and chugging this equation. So then looking at question 8, you'll be predicting whether allele T, little t, will eventually be eliminated if selection persists. So you'll be going through finding which one of these relative fitnesses for these genotypes are smallest, looks like smallest, largest, and in the middle. So this is a true-false question where you'll be looking at if allele little t will not eventually be eliminated if selection persists. So then question 10 goes over another application question where you have the different genotypes. Here it's N1 and N2 are the two different alleles. And then the current and expected future frequencies. So comparing these, you'll be asked the question based on these numbers, which genotype of the giant turtles does natural selection favor in this environment? Then finally, question 11, we'll look at the absolute fitness for these insects. It looks like the initial number of genotypes, big A, little a, and little a are 200, 400, and 400. So you're already given the frequencies of each genotype out of, it looks like 1,000 insects. So after an environmental change, the surviving individuals are quite different. So you're going to have to recalculate the ratios because it looks like the total number is going to be slightly less. Then you're given the average number of offspring per individual is 5. So you just have to use the equation that's provided in the PowerPoint as well. And then finally, the last step that you'll be doing is calculating the relative fitness. Once again, you'll be using AA as a baseline for the highest absolute fitness. Well, big A, big A. But yeah, those are all of the questions. Once again, if you have uh, any inquiries about this recitation, feel free to contact one of your TAs. Specifically, TA Wansheng will probably be able to give the best help because he actually developed this recitation from scratch. Um, but besides that, I'll stop screen sharing and best of luck on recitation 7.